This series of slides is designed to help you understand the reason why we want to have classical assumptions about the error term in a regression model. So we want to know what happens if these assumptions are satisfied, what the nature of these assumptions is exactly, and what happens if one or more of the assumptions is not satisfied. So that will be our beginning point in our discussion of the classical assumptions. So here are the 7 classical assumptions taken as a group. We're going to argue that the assumption that the model is linear, correctly specified, and we'll talk about what that means, and has an additive error term is going to be important. The error term will be assumed to have a 0 population mean. All of the x's, or explanatory variables, are going to be assumed to be uncorrelated with the error term, and we'll talk about what happens when that's violated. In some sense, this is one of the more problematical violations if in fact this assumption is not met. We're going to assume that the observations of the error term are uncorrelated with one another, which means that we have no serial correlation. This property is sometimes also said to be no autocorrelation. They're used interchangeably. And we're going to assume that the variance of the error term is constant. If it's non-constant, we say that there is a heteroscedasticity problem. Constant variance of the error term is called homoscedasticity. We're going to rule out one of our x variables being a perfect linear function of the others. Okay, so we talked about this the other day in the context of dummy variables, and we'll use that example again today. And finally, we're going to assume that the error term is normally distributed. We're going to justify that in part with the central limit theorem. Okay, so to give you an idea of what's to come, if the first 6 of these classical assumptions are satisfied, we're going to be able to make the argument that ordinary least squares, which is how we come up with our estimates for a regression model, ordinary least squares does about the best job of any possible estimation technique that would be available to us. There is no better way to estimate a regression if 1 through 6 hold. 7 is going to be added because if we can claim that the error term is normally distributed, we're going to be able to assess more readily how reliable our estimated parameters are for making inferences about the unknown population parameters. That is to say, we're going to be able to test some hypotheses and judge how good the estimates are from our equation and how likely it is that they reflect the true population parameters. Okay, so we're going to explain each one of these one by one. So the first one we're going to talk about is linearity, and students sometimes get confused. They sometimes think that we're talking about linearity of the x's, and that is not the case. So the assumption of linearity here has to do with linearity of the coefficients. So the coefficients are the betas in this particular example. We've used alphas, sometimes we just use letters, but in this particular example they're betas, and these betas appear not as exponents. The betas appear not with exponents either. They don't appear as beta 1 over beta 2, so there's no fraction. And so we can argue that the model as stated here is definitely linear in the betas, linear in the coefficients. And that's what we are saying when we talk about linearity of the model. We're also going to add linearity of the error term. So the error term is both additive and it is not logged, it's not raised to a power, it's not part of some fraction, okay? It's not multiplicative. So we have an additive error term and the error term appears linearly, okay? And that's the definition of a linear regression. Note that we could have an x2 squared, so beta 2 x2 plus beta 3 x2 squared. That would be okay. Beta 3 to the log of x2 would be okay, because we're not concerned about nonlinearity in the x's. All right? We're only concerned about nonlinearity in the betas, and we want to make sure that that error term is additive. Okay? Now, what does correctly specified mean? Well, correctly specified is going to have two components to it. The first one is that we have all of the relevant x's in our model. That is, we have not omitted any important x's, which is pretty difficult to do, right? I mean, we often are only semi-informed about whether a particular x should go in the model or not, and so we do run the risk of violating this assumption of correct specification. We're going to think a lot about what the consequences will be if we omit an important variable because we couldn't get the data for it also. So that'll come down the road a little bit. The other part of correct specification has to do with the functional form. So everything here is linear in the x's in this particular case. But what if we're wrong about that? What if the x2 should have been squared? Or what if the x1 should have been logged? Okay, so we're going to assume that we have the correct functional form as well as the correct set of x's, all right? But we could easily be violated, right? So some examples would be of a nonlinearity. Okay, so if we have a yi equals alpha 0 plus alpha 1 over alpha 2 xi, that would be a violation of linearity in the parameters. Yi equals alpha 0 plus e to the alpha 1 x1i, okay, that would be a violation of linearity in the parameters. If we had yi equals a x1 alpha x2 beta e epsilon, that looks like it would be a violation of linearity, but as we've shown before, we can take the natural log of both sides and we can linearize it. And now we have an additive error term. We are linear in x2, sorry, not in x2, we are linear in the beta, and we are linear in the alpha, and so we have satisfied the requirement of linearity. If we were to omit an important variable, okay, if we omitted x2 and x2 was important, all of this x2 would go into the error term, okay? And if x2 was in fact an important and relevant determinant of y, then we would be violating correctness of specification. Okay? If this was the wrong functional form to begin with, and we stayed with it, even in its log version, we would be violating correct specification. So that's the meaning of the model must be linear and correctly specified.